radio wave propagation in urban area. This equation here is a general equation relating the received power at the receiver with the transmitter power, the gain of the transmitting antenna, the total loss here. L is positive here because minus negative, and L should be positive here. Even if you are given L negative, here you should plug L as a positive value. So always use the absolute minus the absolute value of L. L involves all kinds of losses: free space losses, building losses, mountain losses, any other losses, plus the gain of the receiver antenna. So the gain increases the receive power, the transmitter power increases the receive power, whereas the loss always decreases the received power. This is the scenario: transmitter, receiver, receiver here, gain of the transmitter, gain of the receiver, path loss L. Path loss L may be read from Hatta or Landau model or Okumura or any other model. To find the electric field, we use the equation we already derived, this equation here. We use this equation here. If we know the loss, we know EIRP, P transmitter, G transmitter, and we know the frequency, we find the electric field from this. Okay, we can find the electric field from this equation. This is an example. If the path loss L is equal minus 90 dB at a frequency of 300 megahertz, this is the frequency, and the loss is minus 90 dB. From Hatta model curve, the loss is minus 90 dB here. This minus 90 dB is taken from Hatta model curve. The transmitter power is 15 dB and the transmitter antenna gain 10 dB, the receiver antenna gain 3 dB. Then P received equal PT plus GT minus L plus GR. This is this equation here, this equation. PT is 15, GT is 10, and L with head always we put minus absolute value minus 90, and G receiver is 3 dB. It is 10, 15 plus 10 25 plus 3 28 minus 90 plus 28 is 60 minus 62 dB. This is the received power in dB. If we want to calculate the electric field in dB microvolt per meter, we use the equation, general equation we derived, this equation here. Now 77.23 EIRP in dBm is equal to here PT plus GT 15 plus 10 25 plus 30, because dBm it will be 25 plus 30 55. We have here EIRP is 55 dBm, and 20 log F in megahertz is F is 300 mega. So 20 log F 20 times log 300 megahertz is equal to 3 300 megahertz log times 20 equal, the answer is 49.5. Oh, this is 49.5, and L is 90 dB. We put here 90 dB. L is 90. That is minus 90. To find the value, it is 77.213, 77.213 plus 55 plus 49.5 minus 90 equal to 91.76. 91.76, because we put here the approximate value. It's not 49.5 exactly. If we put the exact value, we will obtain 91.76 dB microvolt per meter. This is the level of the electric field near the receiver. Problem here, example. A system with 56 dB EIRP. Transmitter. This is the transmitter, because the EIRP is P transmitter plus G transmitter in dB, and operating at a frequency of 902 megahertz, requires 50 dB microvolt per meter electric field. This electric field strength. Use figure 7.9 to estimate the range. If the transmitter, we want the range. Range means distance. We want the distance. If the transmitter height is 100 meter, we want the distance using figure 7.9. Now, figure 7.9 is valid for only for 62.15 dB EIRP. The EIRP here is 56, so the difference is 62.15 minus 56 here. This is the difference. Now we add the difference to the signal level, which is 50 dB here. As you can see, 50 dB micro. So we add this to 50 dB micro to obtain the electric field. If EIRP is 56, we obtain 50 dB. If EIRB in the curve is 62.15, we will obtain higher value. It will be 656.15. The difference between EIRBs plus the measured value. So this is the value that we would obtain if the EIRB is 62.15, because we cannot use the curve unless the EIRB is 62.15. So we put this value now in the curve 56.15 to obtain the distance. So let's go to figure 7.9. This is figure 7.9. The value was 56, 50 here, 56 point something. Here, approximately. Let me just go back. here the value was 56.15, 56.15. Okay, 56.15. $56.15 is something like that here. Yeah, it's approximately here. Oh, the distance is around, as you can see, it is around 10 kilometer. It's 10 kilometer. Let's figure 7.9 is because the transmitter height is 100 meter, of course. As you can see, transmitter height is 100 meter. Here you can see that the transmitter height is 100 meter, so we are working on this curve here. Okay, and the distance is 56.15, something like that, as you can see. So the distance is maybe 10.1 here, 10.1, 10.2. This is the distance. This is the distance. See, it's around 10.1 kilometer. 56.15, around 56.15. This is a linear scale, and this is a log scale, and we use the 100 meter. So the distance is 10.1 meter. This is the distance. The answer is, as we have seen on the curve, the distance is 10.1 kilometer. Another example, the median signal measured on a suburban street at a 20 kilometer range, the distance is 20 kilometer. Distance 20 kilometer. This is the distance 20 kilometer from a 100 meter high transmitting antenna. So this is the base station height HB. This is base station height 100 meter HB. Is the signal level is 29.8 dB microvolt per meter. This is the electric field at the receiver, near the receiver. This is electric field near the receiver. Electric field near the receiver. Find the EIRP from the same figure, 7.9. Now we use the distance is 20 kilometer, and the base station height is 100 meter, and the electric field is 29.8 dB micro. Find EIRP. The distance is given, and the base station height is given. We can find the electric field there, but there the value is valid for EIRP of 62.15. Let's see. We use again this curve of 100 meter, this curve 100 meter base station height, and the distance is 20 kilometer. Here is the distance. This is the 20 kilometer. We use this distance here, and here is the curve. You can see. Or we can read directly the electric field. it is maybe between 46, maybe around 46 dB micro. If you use the ruler, you will get a more accurate answer, but this value is valid only for 62.15 dB MEIRB. As you can see here, the electric field. Okay, we obtain the value of 46 of 45. Here we obtain 45 dB microvolt per meter from the curve. It is 45 or 46. I have used a ruler here in this question, and the more accurate answer was 45. Now this is valid for only EIRB of 52. Our EIRB, our signal level received is lower than this. This means that our EIRB is lower. If you receive lower power, this means that your transmitter power is also lower. So we subtract 45 minus 29.8. The difference, we have to subtract it from 62.15 to obtain EIRB for our transmitter. It is 62.15 minus the difference between them, between 45 and between the received power. If the EIRB is 62.15 and the received and our received power, the difference, this means that our transmitter has a lower power and lower gain antenna. So 62.15, this minus the difference, this minus this, and we obtain, as you can see here, it is 62.15 minus 45 plus minus minus plus 29.8, and the result is 46.95. As you can see, this is dBm, this is EIR. Another problem, using figure, the same figure 7.9, find the path loss at 300, 600 and 1200 megahertz from an antenna at 200 meter height. We want the path loss L. We want the path loss L. And we are given frequencies. And we are given also base station height. The path loss from figure 7.9 is given by this equation, 139.4 plus 20 log F minus E. F is given, you plug in 300, then 600, then after that 1200. And E is given in terms of the range here. So we put different ranges to obtain electric field, and you put electric field for here, and you put frequencies to find the path loss. So you can draw a curve for the distance against the path loss, or the frequency against the path loss with the distance as parameter, or distance with path loss with the frequency as parameter. Now, propagation within, near and into buildings. I will stop here and continue later on.